Okay, in this video we're going to look at fundamental trigonometric identities. We're going to start with this diagram here. So we've got our angle theta in standard form. So we've already seen that so with theta in this form, sine theta is going to be opposite of adjacent, because theta will be x over r, and tangent theta is going to be y over x. Now, by Pythagoras theorem, by Pythagoras theorem or rule, we know that x squared plus y squared is going to be equal to r squared, because we've got a right angled triangle there. Let's call this equation 1. Okay, now we are going to divide 1 by r squared. Now remember, r can never be equal to 0, so we can do this without any anticipated problems. So we're going to have x squared over r squared plus y squared over r squared is equal to r squared over r squared. So this we can write on the left hand side as x over r all squared, y over r all squared is equal to 1. Then from our formulas here, we can see that x over r is cosine theta, y over r is sine theta. So this here is simply implying that cosine theta squared plus sine theta squared is equal to 1. Then for brevity, we are going to lose the brackets, so we're going to write this as a sine theta squared plus cos theta squared is equal to 1. So this is going to be our first formula, which is called the fundamental identity of trigonometry. So this formula is called the fundamental identity of trigonometry. And since this is always true, so we're going to say this is true for all values of theta. All right. Now next what we're going to do is we can divide the formula number 1 by y squared. Or maybe we're going to divide it by x squared first. Okay, so let's say next divide 1 by x squared. Okay, so we are going to have, so remember, there is our formula 1, so we're going to have x squared over x squared plus y squared over x squared is equal to r squared over x squared. This one is going to be true for so long as x is not equal to 0. because if x is equals to 0, then we're going to have a problem because we don't want to divide by 0. Okay, so long as x is not equal to 0, this side, this one is going to be 1. This is going to be y over x all squared. This is going to be r over x all squared. Then this is going to give us 1 y over x is tangent. It's going to be 1 plus tangent squared. R over x is the reciprocal of cosine. So cosine is x over r, so r over x is the reciprocal, which is the secant. So this is going to be secant squared theta. Now this formula is going to be true so long as theta is not an angle along x equals to 0. So remember, we want x to be different from 0. Well, where is x equals to 0? X is equal to 0 along the vertical axis. Okay, so that identity is going to be true so long as x is not along the vertical axis. What angle is along the vertical axis? There are two angles. This angle here is 90. Okay, and then this angle here is 270. So what we're going to do is we're just going to say so long as theta is an angle different from 90, and then we are going to add multiples of 180. So plus 180n, where n is an integer. So for instance, 90 plus 180 is 270, and then so this is making sure that all the coterminal angles of 90 plus 180 are included. Okay, lastly, we can divide dividing by y squared now. So first we divided by r squared, then we divided by x squared. We're now going to divide by y squared, and we're just going to state the result here. Dividing by y squared is going to give us 1 plus cotangent squared is equal to cosecant squared. This trigonometric identity is going to be good so long as we are away from the horizontal axis. So along the horizontal axis we've got 0, 180, etc. So we're going to say as long as theta is not equal to 180 degrees times n, where n is an integer. Okay, so these are our three fundamental identities of trigonometry, which we are going to use below to work out some trigonometric identities. So let's look at the examples. Alright, so suppose we have these examples here that we need to prove. Before we do the proofs, we're just going to state some guidelines in proving trigonometric identities. Guideline number 1, it will typically be useful to express everything in terms of sine and cosine. Okay, so if you just write everything in terms of sine and cosine, that will be helpful. Also, if we have got fractions, sum or difference of fraction, we are going to express them as a single fraction. Single fraction. and then the last one, it usually helps to work from the side that looks complicated, from the complicated side. Alright, so let's look at example A then. So in example A, we have got 1 minus cosine squared. Which symbol are they using? Theta. 1 minus cosine squared theta into 1 plus cotangent squared theta equals to 1. So this time we're going to work from the left hand side because it clearly looks more complicated than the right hand side. So we have got 1 minus cosine squared theta times 1. Cotangent is the reciprocal of tangent. Tangent is sine over cos, so cotangent is going to be cos over sine, so cotangent squared is cos squared theta plus over sine squared theta. Then 1 minus cosine squared theta. We come to our fundamental equation here. You can see that if you take cosine squared theta to the right hand side, then you're going to have sine theta remaining this side, 1 minus cosine squared theta. So 1 minus cosine squared theta is just sine squared theta, so that we can write as sine squared theta cosine squared theta over sine squared theta there. Before we sort of write this as one fraction, we are just going to see what happens if we multiply out these brackets. Multiply out these brackets. Sine squared theta times 1 is just sine squared, and then you're going to notice that if you multiply this term by this term, sine squared is going to cancel out, so we're just going to remain with cosine squared. But then sine squared plus cosine squared is equals to 1, and so this is now equal to the right hand side. Okay, so going on to example number B now. In B we have got 1 over 1 plus sine theta plus 1 over 1 minus sine theta. This is equal to 2 times secant squared theta again. The left hand side looks more complicated, so we're going to work from the left hand side. And also on the left hand side we've got a sum of two fractions, so straight away you're going to write that as a single fraction. The LCM is going to be the sum of the two denominators. So then this is going to go into that this many times, so we're going to have 1 minus sine theta here, and then this plus comes down here. This one goes here this many times, so that's going to be 1 plus sine theta. The signs are going to cancel out in the numerator. Put minus sign here plus sign here, so we're just going to have 2 over 1 minus sine squared, difference of two squares. However, 1 minus sine squared is cos squared, just like 1 minus cos squared is sine squared. So we can write this as 2 over cos squared. 1 over cos squared is secant, so 1 over cos theta is secant theta, so 1 over cos squared theta is secant squared theta, and that already is the same as the right hand side. See, we have secant to the power 4 theta minus secant squared theta. We are told this is equal to tangent theta to the power 4 plus tangent theta squared. Again, want to work from the left hand side. This time the two sides, you couldn't really say the left hand side is more complicated than the right hand side, so it's just up to us to choose which one. But basically we want to write these two terms in terms of tangent. First thing we can do is we want to factor out secant theta squared, and then this is going to be secant squared theta minus 1. Then going up to one of the formulas that we derived here, we can say that if you take 1 to the other side, then we're going to have tangent squared theta is secant squared theta minus 1. So secant squared theta minus 1 is tangent squared. So we can write this as secant squared theta times tangent squared. And then using that same identity, 1 plus tangent squared is secant squared. So we can write this in terms of tangent. So secant squared is just 1 plus tangent squared, and then times tangent squared theta. So this is equal to tangent squared theta plus tangent theta to the power of 4. Okay, the last example we're going to do is D. In D we have got tangent A minus sine A all divided by sine A cubed. This is equal to secant A all over 1 plus cos A. We are going to work from the left hand side. The first thing we note here is that on the right hand side you've got cosine here and secant here. So we know that secant is 1 over cosine, so everything this side is in terms of cosine. So we'll keep that in mind as we work out the left hand side. The numerator, we're going to write it in terms of sine and cosine. So this here tangent is sine A over cosine A, and then minus sine A. So that's just the numerator, and there is the denominator. Now we're going to notice that sine is common here, so we can factor out sine and divide into this. So if we do that, we're going to have 1 over cosine theta here minus 1. Then we're going to have sine A over sine cubed A. Then this we can write as one fraction. If we do that, gonna be cos A, then theta. Then we're going to have 1 minus cos A there. That one is going to be 1 over sine squared A. Now remember, the right hand side is entirely in terms of cosine, so we're going to want to write this as a cosine. So if we do that, we are going to have 1 over 1 minus cosine squared A. But then this is a difference of two squares here, which we can factorize. So we're going to have 1 minus cosine A over cosine A times 1 over 1 minus cosine A into cos 1 plus cosine A. Then this will cancel out with that, and then if we move this cosine A up into the numerator, it's going to become secant. So, but what we can do is, for starters, we can write this like this, and then move the cosine A into the numerator, and it becomes that. And so this is now the same as the right hand side. Okay, so let's give you 3 to have a go at. Alright, so just have a go at these ones here. In E, you've got 1 minus cos A times 1 plus secant A is equals to sine A tangent A. In F, you've got 1 minus sine squared phi over 1 plus cos phi is equals to cos phi. And then in G, got 1 plus cos x over 1 minus cos x. Take away 1 minus cos x over 1 plus cos x. This is equals to 4 cot x cos secant x. So if you just want to pause the video and have a go at them, and then later you can compare with our answer. Alright, so I hope you've now attempted these. If you haven't still, do pause the video, attempt them before you look at our answers. Right, so for A, we have got the left hand side is clearly more complicated, so we're going to start from that side. The first thing I want to do is we're going to write this in terms of sines and cosines. Then we're going to combine this into one fraction, and then if we multiply the numerators, we get 1 minus cosine squared. But 1 minus cosine squared is sine squared. Then we can write this as sine over cos times sine. Sine over cos is tangent. Then this is now the same as the right hand side. In F, again, if we start on the left hand side, we have got two fractions here. So the LCM is 1 plus cosine phi. So this is going to go 1 plus cosine phi squared here, and this is going to go once, so just have sine squared there. If we move this and group it with the 1, so 1 minus sine squared is just cosine squared. This term remains the same. Then we factorize cosine here, and then these two terms are not going to cancel out, and so I've got cosine phi. Again, for g, if we start on the left hand side, the obvious thing to do is to write this as one fraction. So we do that here. Then the numerator is a difference of two squares. We expand these two using the binomial. Then when you open brackets here, you're going to notice that the ones will cancel out and the cosine squared terms will cancel out, and then these two will add up to 4 cosine x. Then if we split this into cosine over sine, then 1 over sine, cosine over sine is cotangent, 1 over sine is cosecant, and so this is the same as the right hand side. Okay.